All right, welcome to our free GMAT prep hour for January 9th, 2023. I'm Dmitry Farber. Today's theme is problem solving, and specifically in quant, what we do in the first 30 seconds of a problem. So I'm worried less today about the challenge of the problems. Some of these are challenging. Some of them you might find kind of on the easier side. But I want you to think about what you know right away, what you can notice, what are you able to eliminate, and what you write down on your paper. And a lot of this is about reducing error, because I see a lot of people who say the same thing to me. They say either, I spent too long on a problem, I knew I could do it, and I just wasn't getting the answer and I didn't want to let it go. And that's a real danger on this test, that we spend 4 minutes on a problem and it messes us up for the rest of the section. And so it's very important that whenever we have to choose between being on time and being right, we keep choosing to be on time. It's more important to be on time than to be right on any given problem. However, I think what happens is people set themselves up wrong at the beginnings of problems. And then they've already kind of lost the battle and they don't know it. And they're laboring at something the wrong way or answering the wrong thing, and they have no idea. The other thing I often see is that people are missing problems that they completely know how to do. And when I go over the problem with them, they understand it. They have the relevant content knowledge. They're able to set it up and solve it clearly. And they go, oh, wow, I just don't know how I got that answer. Or I made a mistake. It was just a careless error, but I don't know how to avoid that. And so a lot of that, not all of it, but a lot of that is taken care of right at the beginning. What am I looking for? What do I have on my page? How can I get rid of answers that don't make sense so that if I then calculate and get that answer, I go, no, that's not it. Often when I'm doing GMAT problems at my job, I have an unfair advantage, which is that I already know the answer to the question. And so sometimes I catch my errors because I already know that the answer is, say, B, and therefore if I get something else, I know I've made a mistake. This is, of course, not something you have access to when you're taking the GMAT, or usually even when you're doing practice problems, although it might happen when you're reviewing. So instead, you want to have an idea of what you can expect out of the answers, what answers make sense and which answers don't, so that you're more likely to notice when you make mistakes. But also when you slow down and really understand what's happening in the first 30 seconds, you can decide when to let a problem go. Is it too hard? You can decide what strategy you might want to use that's really efficient. And sometimes you can actually get to the right answer. And so one reason I selected some problems, and again, not to stress the ease of the problems, some of them are challenging, but I chose some problems that we might be able to answer very quickly. We might be able to be done in the first 30 seconds or 1 minute. And the point is not that that's what you should experience on the GMAT. If you're getting a bunch of problems you can do in 30 seconds to a minute, the test will ramp up until you're not getting those anymore. But if we can get really solid like that, then that gives us room to breathe on other aspects of the exam. So let's try some things. So yeah, a question about that. When do you know to work backwards? Well, it's funny you say that, Rob. When I was planning this workshop, one of the things I was thinking I might highlight is deciding about working backwards. And what I realized is that I looked at a lot of problems that I wanted to use. I was kind of surprised how rarely I actually wanted to work backwards on them. And don't get me wrong, it's a valid strategy. And when it works, it almost feels like cheating, like legal cheating, because you can just say, oh, well, it's 40 is too small and 60 is too big. So, oh, look, it's 50. Look at that. And that's really nice when it happens, but it doesn't happen as often as we'd like. So it's not usually the first thing on my mind, but it's certainly something we'll talk about as we look at some of the answers. How do we tell when we can work backwards? So that's an excellent question. And again, it's something that we want to look for. One thing I'll add is that this process we're going to look at for the beginnings of problems is something you can also do later when you're reviewing a problem. This is something, in fact, that you really should do. I would almost say that if you're not doing this, you're studying wrong. That's how opinionated I'll be about it. And what I'm saying is, when you finish a problem, you should do it again, and maybe do it again another time, ideally before you even know what the answer is, and go back and say, all right, well, I got B, but is there a way I could have gotten there faster? Or is there something I could have noticed? Right? Today I was doing a problem with someone, and we did it a very hard way. And then I was showing how you could see an easier way to do it. And one of the questions I had was, okay, can you see why this would have occurred to you? Is there a way to know you could have done it this easier way? What signs were there? And that's a lot of what we're looking for. And so one of those things might be, hey, is this a problem I could solve another way, such as working backwards? So we'll look at a lot of that. So probably the most standard thing that people are used to doing early in a problem is estimating. And certainly that's one of the valid tools we want to have in our toolkit, is we want to be able to estimate an answer. So I'm going to start with the area for which that's maybe the most familiar, which is geometry. When we're given a geometry figure, we aren't always guaranteed that the figure is drawn to scale, although usually in problem solving questions, it is drawn to scale. And even if they don't guarantee that, sometimes we can just tell that the picture is roughly accurate because it looks, they say it's a square and it looks like a square. So if it's off, it's not off by very much. So on those problems, we can often estimate. And even when we don't have a picture, we can make our own and use that picture to get an idea of what we're dealing with. So I want to start with some of that. That's one of the natural things we could do. And it's something we don't always think about enough. Often I see that once people have been studying the GMAT for a while, their data sufficiency gets much better because they understand the process of that kind of new topic. But then their problem solving starts to suffer. They're able to get some fairly hard data sufficiency questions right, and then they're just having trouble closing the deal on problem solving. And sometimes I see people's accuracy dipping really low on that side of things, which is unfortunate since it's the majority of your quant section. So if we can find ways to narrow things down, then even when we're stuck or we make a mistake or we're guessing, we're still, guaranteed a certain baseline of, maybe 1 out of 3 instead of 1 out of 5. So let's look at a few geometry problems for starters. So in this question, we're given a diameter and we're given an angle length. You may or may not know some rules for this, but they want to know the length of arc ABC. So let's think about a few questions here in terms of what I put up front, right? What do we know here? What do we notice? And what can we write down or eliminate? I may or may not draw this picture. For now, since it's up on the screen, I won't redraw it, of course. But what I might ask is, first, what do you notice about the answer choices in relation to what they want from us, right? Is there a way to narrow down these answers, or are there any traits we can use to cut out some of these answers? Sometimes what we'll do if we're not sure is we'll just start going in and drawing stuff. Say, okay, well, I have this picture, that I've maybe redrawn, and then the diameter is 36. So what's the length of ABC? I could write by 36 here, okay? Or I could draw it here, kind of cutting the figure in half. Or I might not draw it at all. Instead, I might say, hey, if I know the diameter is 36, there's something else I know, right? What can I immediately calculate that's relevant if I know the diameter? I can get the radius, right? So the radius is 18, right? And then what can I do with the radius or with the diameter, right? If they want to know the length of arc ABC, they want to know this. What's the most relevant measure I could think about? So if I think of what do I know? Oh, that's really funny. Right? That's really, I love that I started this class with a mistake. And it's my question that I'm featuring, right? So this is beautiful. I love when my mistakes illustrate perfectly what we want. Look, I'm drawing the wrong arc. Now, whatever else I do will be wrong. I wish I could pretend that I did that on purpose because it's perfect, right? I don't want that arc. They told me I want arc ABC. Look at that, right? I want this arc. And so if I estimate, I'm going to estimate wrong. I got to watch that kind of thing. Okay, beautiful. Okay, so I want the pink one, not the green one. Okay, and then what do I know? I know the radius is 18. That would allow me to find the area, but I don't really care about the area. What measure do I care about if I'm measuring arcs? Yeah, I care about the circumference, and you can call that 2 pi r, but honestly, you know what I'd call it? Pi times the diameter. And whoever invented 2 pi r, I kind of want to, give them a piece of my mind about that, because circumference is really just diameter times pi, which is 36 pi. So the radius is 18, that's true. But what I kind of care about is that the circumference is 36 pi. So then what I know is that this arc, without any particular rule attached to it, I know this arc is most of it, right? I know this arc is most of it. So now I might think about, all right, what can I eliminate? So I'm seeing a comment of so D. Well, then how do we know that it's, say, not C, right? What's our way of narrowing down? So what are the answers that are simply impossible, right? And then what are the answers that, maybe are more or less probable? That's what we want to think about. Yeah. A doesn't seem possible because there's no pi in there. Now you could say, well, it depends on what the angle is, right? Maybe I could have 8 as some fraction of 36 pi. That's true, but that would involve the fraction of the circle being something over pi. If you've messed with this much, you'll know that probably doesn't happen. But there's another reason we can know this without even worrying about the pi business, right? What would just half the circle be? Half a circle would be 18 pi. So at the very least, what we know is that our answer, it's got to be in between 18 pi and 36 pi. It's more than half for sure, right? The picture can't be that off from scale. If I look at this angle, it looks like a 40-degree angle. Maybe it's really a 32-degree angle or something, but it's not a 90-degree angle, right? It's not that far off. So this is a reasonably accurate picture. We've got most of the circle. And so we can get rid of anything below 18 pi. And of course, anything that's bigger than the whole circle. C and D are pretty close. And at this point, if I were just guessing, I would just grab one of those and move on. From here, I'm going to have to lean on what I know more, which is how do I find it? But this is what I want, right? I want a fraction of 36 pi. So that's kind of what I might accomplish in the first 30 seconds. From there, I have to know a way to solve. Do we know a rule for this? There's a rule basically that says if you have a central angle, right? Imagine this being the exact center. And you have an inscribed angle that has those same endpoints, the central angle will be double. So if the outside angle is 40, this is 80. And that 80 is proportional to what fraction of the circle we have, right? So the AC part, the part I started to highlight, the AC arc is going to be 80 out of 360 of the circle. Arc ABC will be the other 280 out of 360 of the circle. Now, in case you're thinking that you need a calculator at this point, look how nicely the math is designed to work out. They know you don't have a calculator. They have to make life easy on you. So arc ABC will be 280 over 360, also known as 28 over 36, times the circumference of 36 pi. And so we can do some quick cancellation. The zeros cancel, the 36s cancel, and we're left with 28 pi. Okay, so it's C. It would be pretty hard to eyeball C versus D, I think. Maybe someone has a way of doing that. But those are close enough where at that point we have to calculate. And so that's one thing you want to notice as you're looking at answers. How close are they? Is it the kind of thing where estimation is going to get me there, or do I have to actually know, right? If you asked me to say the population of different countries, right? What's the population of France, of India, right? Of, Monaco or something like that, right? I might not know off the top of my head, but I might know to an order of magnitude. And so if you give me multiple choice, I might say, well, of course, France has more than 100 people, and less than 1 trillion people. Okay, I can narrow that down. But if the answers are all the same size, and I have to know, what the units digit is, I don't know who in France was born and died today. I don't know. I don't know how that level of precision. And so when it gets more precise, then as we have to get in there and calculate and find things. Okay. Questions on that? So no, the question is about the what angle to use. Well, if you keep drawing this out, you'll see the inscribed angle maxes out way before 360, right? You can't have a 360-degree angle, right? And you can't come close to one drawn inside the circle. Whereas this circle, you can, in a sense, have a 360-degree angle. It just means returning where you started, right? So think about where half of the circle would be. If I were to draw a line straight through the center, that's a straight line. It's 180 degrees. That's half the circle. So 180 is half. 360 is all. 90 is a quarter, right? 80 is just under a quarter. So we have just over 3/4 of the circle. That's another way to do it. We have just over 27. Whereas the 40 wouldn't correspond to the total 360 of the circle. So no, we use the central angle, not the inscribed one. Cool. Let's do some more. Here's a circle inside a square that has an area of 50. Okay, well, now it's about area. I know how to find the area of a circle. I know how to find the area of a square. I just have to find a connection between them. These aren't too crazy, but the biggest thing I should do immediately is notice the answers and say, okay, what can I eliminate? All right, so if the square has an area of 50, what answers are out entirely? This is a known relationship. In fact, it's one you might even have memorized. But we know that the area of this square circle has got to be less than the area of the square. It's inside it. So none of this, it's 25 pi, 50 pi, because this is, a little over 75. This is a little over 150. There's no way those can fit inside a square with area of 50. 625 over 16, you're not supposed to have memorized that, but you'd say, okay, 50 would be like, around 15 pi or something like that. So as long as this is more than 15, then we know this is too big. And 15 squared is 225. So 625 is way more than 15, right? Yeah, so we know this is more than 50 is all we care about. And yes, this modifier, a square that has an area of 50, well, there's two things here. Yes, that modifies square. So that's, sentence correction stuff. But also, if they told us the area was 50, then they couldn't ask us for the area of the circle, right? So we know it wouldn't be a trick question. Like the GMAT will never basically tell you the circle is 50 and then ask what the area of the circle is, hoping that you're like fooled by the grammar or something like that. The GMAT's just not that kind of test, right? So that would never happen. So they're being straightforward in that sense. They're not that sneaky. Okay, so the square has an area of 50. I could sit there trying to find the side of the square, but I'd rather not. So using just logic at this point, we might say, okay, roughly, what could the area of this be? All right. So both of these have a pi on top. So we can still approximate, even though pi is a little more than 3. If we said, hey, this is about 75 over 4. And this is about 75 over 2. One of those is twice the other. Go ahead and pull this in. Which of those do you think is more realistic? The area of the square is 50. It might help to finish this math, right? 75 divided by 2. It's a little less than 40, right? So if you want to be precise, it's about 37.5. I'm saying about still because, of course, 25 pi is a little more than 75. And so then this would be half of that. So it'd be like 18, right? So if the square is 50, the circle's got to be more than 18, right? Wouldn't you figure that half a square would be 25 and there's got to be more than that? We just can't have A. So we could prove this, right? One thing you can do that we tend to do when we see variables in the answer choices, but we can do even when there are no variables, is we can make numbers up. Now you might think, well, why would we make a number up when they've given us a number? Well, we might make numbers up if these are hard to work with. So what if I said, forget this thing about the square having an area of 50. I'm going to make the square have an area of 100. And you might say, what? It doesn't have an area of 100. Okay, let's just say it does. Let's say the square equal to 100. What would the circle be? Well, the circle would also be 10 tall, which would mean it had a radius of 5. Now, this is a lie. These clearly aren't the correct numbers, right? So sometimes I'm making up some BS, right? But I can then say, okay, the circle is pi r squared, right? Okay, so the circle over the square is equal to 25 pi over 100, which equals pi over 4. So what we know is, and this is provable for any circle and square, if you have a circle inscribed in a square, meaning it's tangent at those edges, it just touches at those, 4 sides, then it's pi over 4 of the square. And so what this tells us in our case is the circle equals pi over 4 times the square. And so the circle is pi over 4 times 50. It's 50 pi over 4, which is pi over 2. Sorry, pi over 2, 25 pi over 2. Okay, so we can prove it that way. I made it, I made the numbers nicer, so I didn't have to worry about proving the real way, right? The real way being that the square has an area of 50. That means each of the sides is root 50, right? Which is a 5 root 2. That's a little uglier to work with. And then the radius of the circle would be 5 root 2 over 2. I don't want to deal with that, so I didn't. Right? I made it simpler. So any circle inscribed in a square is pi over 4. Now, 2 questions about being drawn to scale. First, although not drawn to scale is a problem on the GMAT, it's not as common a problem as people think. Typically on problem solving, the pictures are drawn to scale. And here, that's a completely irrelevant concern because I can see that the circle is inside the square. I'm not relying on the picture in any other way. I don't even need this picture, right? The picture is not really relevant. So we actually don't always have to worry about the picture being wrong. It's often fine. And even when it's not fine, it doesn't always matter, right? We've got to make our own picture anyway, and we've got to prove our things with facts anyway. So I wouldn't worry about the scale here at all. Okay. So one thing to think about is when you have very predictable relationships, like a circle inside a square or a square inside a circle for that matter, if you can choose easy numbers or numbers that you know to find that relationship, then you can use that relationship to find what you really want, the specifics of the problem. Okay. Here's a different one. And one thing we might notice is a difference in the answer choices. Right. In this one, we had pi in all the answer choices. We were being asked about area, but also we had very large leaps of magnitude between answers. B is twice A, right? And C is twice B, and D is twice C. And I don't know exactly how many times D E is, but it's large, right? It's too large anyway. It's too big to be the area. The answers here are much closer together, and that creates 2 problems for me. One is that it's harder to say that any of them are ridiculous, right? Oh, they're way too small or way too large. 2 is that it means I may have to calculate with some precision, right? I may not be able to estimate at all. And those are related problems, obviously. I might be able to look at some features. Maybe I expect the 25 or the 24s or the 12s or things like that. So what I might notice in the first 30 seconds is very similar answers. So it's going to be hard to estimate. However, there's one outlier. Which answer should I cross off right at the beginning? I don't know if I can easily prove that it's not half. I may be right, I may be wrong, but these answers are all very close to half. So I'd be nervous. So those of you who are saying 1/2, be careful. I'm not saying 1/2 is the right answer, but 24/49 is basically 1/2. 25/49 is basically 1/2. Even 7/12 is basically 1/2. They're all around a half. So a half is not a wild answer. There's a wild answer. There's an answer that's just like, no way it can be right. And you could argue that about all the wrong answers because they're wrong. But 3/12 is a quarter, right? That squared is just not taking up that large a portion, right? This is only a quarter. And visually, again, you could argue, is this drawn to scale? It is drawn to scale. First, because they don't say it isn't. But second, I can tell that if I have a square and it has sides of 3 or 4, then it's all going to be symmetrical. Whatever this side is going to be the same as this side, this side, this side. And I can actually draw some things out about this and see, how much this takes up. Okay, so I would get rid of a quarter. So are we asking, is that white square a quarter of the larger square? No, definitely not. So this is one thing to work on, right? What you notice, what I notice, what someone else notices might be different. To me, I just look at things and I say, well, that's not a quarter, it's much more. You might not agree with me, right? So we got to be able to prove it with numbers. Now, another thing I might notice is what they're asking for. It's really easy to do all the work and then answer the wrong question. So which part do they want? They want the shaded area. And I'm very, very prone to forgetting things like that. So what do I do in the first 30 seconds? I write it down. And what I might even write is shaded equals unshaded over total. Right? And I'll write that down right at the beginning. I could even fill in the total and say, okay, I know that it's a 7-inch square. So that means its area is 49. Now, does that mean the answer has to be one of the ones with 49 on the bottom? Not necessarily. Oh, look. What did I put? Wow, I'm just really, someone's got to yell at me. I said shaded equals unshaded over total. That doesn't make any sense, right? Sorry, what I want is, I want shaded over total. Wow. Okay, you got to keep an eye on me. You got to keep an eye on me. I want shaded over total. Which means I want the total minus the unshaded over the total. Let's write that correctly. And so one thing that I've been illustrating really capably for you today is that we can ruin the whole problem right at the beginning, or we can set ourselves on the path for the right version. So we have to make sure we're doing that. And you might take that for granted a little too much, like I sometimes do, and be fast there and think, oh, this is easy, it's fine, when it's not so fine. So what I want is total minus the white over the total. I know that the total is 49. I want to know the total of the white so I can take it out. And I'm going to know that this is 49. Now, at this point, I might strongly suspect that the answer is B or D. And in fact, you can imagine the test writers are there going, haha, if the answer is B, some people are going to choose D because they're going to choose the wrong one, shaded versus unshaded. And vice versa, if the answer is D, some people are going to pick B. C is a less of a fun trap because if the shaded answer is a half, so is the unshaded answer. So if you mess up, you'll still get the right answer. That's usually not right. So I would be nervous about that for 2 reasons, right? I'd be nervous about the 1/2 because it's equal to the trap answer, right? Would be the same if we did shaded or unshaded. It would also require the white square to be 24.5. And how would we get that? That's a very specific thing. The GMAT tends not to give us things where we're going to end up having to do a bunch of Pythagorean theorem and comes out to exactly 24.5. Seems unlikely. So although I haven't disproven C, I'm nervous about C. So maybe not C. I'm also nervous about E because how is something how is something over 49 going to simplify to 12ths? Well, spoiler, it's not. So partly what I'm trying to say here is not that this is how you must do the problem. You can just solve and do the problem. But if within the first 30 seconds you notice a lot of these things, you're in much better shape and you're much more likely to catch any errors you make. And if you do get stuck, you're much more likely to get the right answer after all. This is in contrast to what I might do on verbal. On verbal, I almost want to do a workshop where I do the opposite and say, stop looking at the answers. Don't look there, because we tend to get fooled by the answers in verbal. In quant, that's less of an issue, and it's more about using our answers to understand and narrow down what we're doing. Okay, so as I said, I am in no way sure that the answer is not C. I have not proven it. It is definitely wrong because I have the answer key, haha, right? It's definitely wrong, but we haven't proven it's wrong. This is just, if I'm on the test, I'm going to say, if the white square turns out to be 24.5, first, that would be kind of bad design from the GMAT's perspective because the trap answer and the right answer would be identical. Second, it would require me to do some math that would end up working out to an area of 24.5. And then what would the sides be? Something really weird. The GMAT doesn't tend to work that way, right? Imagine the side of the square would have to be whatever the square root of 24.5 is, which would be, you know, what's that, 49 halves. And so the side would have to be 7 divided by root 2. That's just not going to happen. It's just not going to happen, right? However, we can prove it. Think of it this way. We know the square has a side of 7. So don't we know what all the pieces are here, right? If this is 3 and this is 4, and the side is the same on all the parts, then okay. Doesn't this then have to be 4 and 3? Right? Because I can't have a 3-3 square, a 3-3 triangle, and a 4-4 triangle that both have the same hypotenuse. That wouldn't be the case. So I have to have 3-4 and 4-3. 3-4. 4-3. You see how I'm getting that, right? If they have to add up to 7, and all these triangles have to be the same, and I know they're the same because they have the same hypotenuse at least, right? Then I have this. And look what the 3 and 4, 4, 3, same thing, right? We know the order because they have to add up to 7. If I have 2 3s next to each other, I make 6. If I have 2 4s next to each other, I make 8. I need 7, so I need pairs of 3 and 4. Right. So if I had these flipped, imagine this was a 4-4 triangle, right? Then this would have to be 3. But wait a second. Then how could this triangle, even if I put a 4 here, how could this triangle and this triangle be the same? They couldn't be. So I'm left with the other version. I have to have that. Okay. So with that in mind, I can find the side. I actually don't even care what all of the triangles are, although it's provable that they're the same. What I care about is what the side of the square is, right? If I have a triangle with legs of 3 and 4, and it's a right triangle because it's in a square, what's my hypotenuse? This is one to memorize. All right. Talk about what can I know? Recognition, we have a 3, 4, 5 right triangle. And the GMAT tends to rely on things where we're not having to do calculations. We're not having to use the Pythagorean theorem. That's what the expectation should be. You should be a little bit spoiled and expect not to have to calculate in this way. So if my area then is of the white square is 5 squared, it's 25. Now I don't want to then jump on D, right? I want to say, okay, let me fill in what I set up. And what I set up is that I'm solving for what's left. Okay, so I have 49 minus 25 over 49. It's very, very, very close to 1/2. It's definitely not 1/4, but it's also not precisely 1/2. What we have in the shaded portion is 24 over 49. It's so close to 1/2 that we can't really see the difference with our eyes. We just have to prove it with our numbers. okay? D is a trap. That's the shaded part. Sorry, the unshaded part. See, you can't even say it. Okay, questions on that? Yeah, the top line has to be 3 and 4, 4 and 3, but we know the order. It has to go around 3, 4, 4, 3, 4, 3, 4, 3, 4. They have to alternate. If I have 2 3s in a row or 2 4s in a row, then I won't get all the same triangle around. So once these are set in 3, 4 order, they all have to be 3, 4 in order, or they wouldn't have the same triangles in all the places. I can't flip any of them, right? These are the exact, these are known. This is how it is. Because if I put a 4 here, I end up with a larger triangle. I get different dimensions. 2 3s doesn't make 7, right? 2 3s make 6. This is a square. It's not some other kind of unspecified quadrilateral. Okay, so using what we know for sure about the shape and its dimensions. Okay. Right, I know, I see what you're saying, but we can't have the triangles be some 3s and some 4s. And since it has to add up to 7, I have to have a 3 and a 4 each time. There's just not another way to do it. Okay. What about this one? What do we know here? This is a very wordy one, right? I've got a 10 by 10 square. I cut it in half along the diagonal, and then I cut it again. And we want to know the perimeter of one of the smallest triangles, so we can just pick one. Let's pick this one. So what do I know and what can I cut out right away? If I want to know the perimeter, what do I know about it before I do a lot of math? I've got a 10 by 10 square piece of paper, so I know this side is 10. So I know the perimeter is bigger than 10, right? That's just that one side, that's out. What about these two sides? What do I know about them really quickly, right? Could they be 10? Could I have a 10, 10, 10 triangle? I know these two are equal lengths, right? Because they're both the same part of the diagonal of the square. In theory, I could have a 10, 10, 10 triangle, but in practice here, I can't have one. Why not? I know these are the same, but they're not 10. I don't know if I've proven they're 5, but I know they're not 10. Because if they were 10, 10, 10, it would be an equilateral triangle. And equilateral triangles are 60-degree angles everywhere, right? We have 60, 60, 60. So if I have instead a 90-degree angle, this is again, and it's a known figure. It's provable what the sides are, but we don't have to actually know it ourselves to get there, right? If this is 90 and this is 10, I know for a fact that these are less than 10. And they're the same number. They're both less than 10. They're the same. So far, what I know is I have 10 plus 2 sides that are each less than 10. So my answer so far has to be somewhere in between, has to be somewhere greater than 10, but it has to be less than 30. Now that doesn't do me a ton of favors because that's most of these answers, right? If you know root 2 is around 1.4, this is about 24. This would be too big. 20 root 2 is, let's see, 28, so 10, 38. This is too big, right? And we know the other sides are less than 10, and so this would be 2 of 10 root 2. So that leaves us with a couple different answers we might think about, right? But we ought also be very suspicious of B. If I have to add 10 plus something else, how's that going to add up to 10 root 2? What number could I add to 10 that would tell me it's 10 root 2? I don't even know that math. I wouldn't know how to do that. This is not going to work because it's got to be 10 plus something. And although, of course, you could say it's 10 root 2 is 10 plus whatever 10 root 2 minus 10 is. But that's not a number we're going to recognize and know what to do with. So it's not 10 plus something. So that's wrong. Whereas C is 10 plus 10. And D is 10 plus, 10 plus 10 root 2. So let me ask you this. We knew that these sides are not 10. Could they be 5? Could I have a triangle that's 5, 5, 10? If you've gotten into geometry much, there's a third side rule that says that can't happen. And one way we can tell is if I have two sides of 5, to make 10, I'd have to flatten them out. You'd have a flat line. You wouldn't have a triangle anymore, right? If this hand is 5 and this is 5, then okay, this third side is like pretty close to 0. 1, 2, 3, 4, 5, 6, but if I get to 10, I would have to have the two sides flat. So they've got to be bigger than 5. Right? So now we can narrow it down a little bit more. We can say, all right, the answer has got to be bigger than 10 plus 2 times 5. But it's got to be smaller than 10 plus 2 times 10. So it's in between 20 and 30. That proves D. Like the other problem we're doing, you could also just get here by knowing your common triangle patterns. But what I hope is useful is that this can help you even when you forget. Right? So this isn't a 6, 8, 10 triangle because these are symmetrical. Like both the sides have to be the same. 6, 8, 10 is a thing. It's double of the 3, 4, 5, right? What this is a right isosceles triangle. And so the pattern for this is that it's side, side, and side root 2. So what these sides are going to be is the very clunky 10 over root 2, right? But that's kind of hard to work with, right? So what I might instead do is find the diagonal of the entire square, right? That might be easier to do. If I know my square is 10, then this itself is a side, side, side root 2 triangle. So I've got 10 root 2. And that means each of these sides then is 5 root 2, which happens to be the same as 10 over root 2. But I didn't have to do that to get the problem right. Yay. And I think that's important to be able to see a lot of these times. That way, even if I mess up or I'm expecting something different, I've knocked down a lot of the wrong answers and I'm more likely to be right. Okay. Let's leave geometry behind now and look at other kinds of problems where we might notice other things in the first 30 seconds. The question was, what's the smallest triangle? I just picked one of the two triangles. They're the same, right? So the smallest triangle is either of these two. That's why they say one of the smallest triangles. I could have drawn this one. Remember that when you're dealing with a square, it's symmetrical. So all these triangles, I could have any of these 4 triangles. They're all the same. Doesn't matter. Right? They'll all have exactly the same dimensions. There's no other triangle to look at. Okay. Something different. So in the first 30 seconds, what might I notice here? One thing we haven't been dealing with so far that now shows up is that the answers all have variables in them. And anytime we see variables in the answer choices, then picking numbers is an option, almost always. And that doesn't mean it's what I should do, but it's something I want to be aware of that I have as an option. I can just pick values of A and B and see what happens. I might also notice squares with inequalities, right? So I might ask, are these numbers getting larger or smaller when squared? And that gets to the other thing I might notice in the first 30 seconds is that I have this weird inequality where the numbers are between 0 and 1. So I know that A is bigger than 0 and less than 1. 1 over b is between a and 1, but these are both, what do we know? A and 1 over b are both positive fractions. So one thing I might do is eliminate based on just one piece. And I could write this down. I could say, all right, let me think about just a. If a is a fraction, right? A is a regular fraction, like a half. What will happen when I square it? When I square 1/2, I get a fourth. And any other regular fraction between 0 and 1, I'll get the same kind of result. It gets smaller. So what I know is that a is larger than a squared. And without looking at the rest of the problem, I can zero in on that aspect of it and start narrowing some things down before I do anything else. So I could say, all right, if I write down on my paper A, B, C, D, E, I could say which ones violate this thing I just found. Look, the very first one, right? A is out. Let's see, B, A is bigger than A squared. C, A is bigger than A squared. D, A squared is bigger than A, that's out. Okay, so I've already gotten rid of 2. So then if I go in and pick numbers or do something else, at least I've narrowed it down, right? I might do that very quickly. I might actually finish the problem this way. Instead of picking numbers, I might just say, all right, well, what about B, right? Right? 1 over b is a fraction. So what does that say about b? B is larger than 1. When it gets squared, it gets bigger. So what I know then is that b squared is bigger than b. Yeah, b is bigger than 1, so b squared is bigger than b. So out of my remaining answers, I don't need to look at A or D. I can write down B, B, C, E, or mark those separately in my paper. I could say, hey, B squared is bigger than B. Let me get rid of ones that violate that. Oh, look, B has B bigger than B squared. That's out, right? Maybe not too surprisingly, the other 2 remaining choices both have B squared bigger. So I've got to think about my remaining thing, which is how A and B relate. Right. But hey, I already know that, right? Because I know B is bigger than 1 and A is less than 1. So B is bigger than A. So now out of my C and E, I could say, oh, look, C says that A is bigger than B. That's out. And I've got this. Now, do I have to do it in this piecemeal fashion? No, this is one thing I might notice. I could jump in there. Instead, if I recognize that I can pick numbers, I could have just right away said, hey, what if A is 1/2? And what if 1 over B is a bigger fraction? Let's say we'll call that 2/3. Then B would be the flip of that. B would be 3/2. And I could just test these. I could say, all right, well then, hold on, let's see. A squared will be 1/4. And B squared will be, what is that? 3 squared is 9/4. And so I can just sort of put them in order. I could say, let's see. B squared is 9/4. That's going to be bigger than B, which is 3/2. One thing I also like about must be true questions is that it means that no matter what you do, the answer has to work out. As long as I'm following what they said, I can't have 2 different answers. It's not like a what's the greatest that could be, what's the, what's the minimum, anything like that. Which of these might be true? It's saying what must be true. So no matter what I pick, it has to work out. Just like with a square and a circle having a certain relationship when they're drawn a certain way. So that's another way of getting to the same thing, right? Saying, oh, I can put these in order from start to finish. That's less multiple choicey. I'm just finding what it is and then looking for the answer that says what I found. But I'm still working with the system, which is I'm picking numbers that allow me to figure this out. Okay, so anytime they say what must be true, you're going to have a different approach from when they say like what could be true. Look at this pair. These are both about divisibility and remainders, but one of them says, what is the remainder when this thing happens? They're telling you about an X and a Y, but they never tell you what they are, and we're not going to find out. But yet there is a specific remainder that we can find. This is a must be true, which means that no matter what I pick, as long as I follow the rules, it has to work. Whereas this one says, which of the following could be, which means I may have to test the answers or know some trait I'm looking for in the answers. Okay. So if I look at this first one, that's one of the things I might notice in the first 30 seconds. This one, there is one, same answer no matter what. Here, I may have to test answers. Right? There's multiple possibilities. Most of them just aren't there, right? So let's look. X and Y X and H are positive integers. When X is divided by 7, the quotient, which is just what you get, is H, right? With remainder 3. So I might write that down. So what are they basically saying? That so 7 goes into H into X H times with 3 left over. What that tells me is X is 3 more than a multiple of 7. So now I just have to say which of these is that true for? Yeah, Rose got it. 3 more than a multiple of 7. This is a multiple of 7. There wouldn't be any remainder if I had one of these. This would have remainder 1 when I divide by 7. This one's a little harder because 57 is less familiar, but wait, 56, isn't that a multiple of 7? So this would also have remainder 1, whereas this would have remainder 3, right? So I'm just saying, hey, which one is 3 more than a multiple of 7? That's all I have to do. If I didn't see this, I could also just test the answers and see what happens, because this is a lot to process. So I might also just say, okay, let me try A. When 7 is divided by 7, the quotient is 1 with a remainder of 0. Okay, that's not right. Okay, when 21 is divided by 7, I get a different quotient, but I still get a remainder of 0. Let me try 50. Oh, I get a remainder of 1, and just keep going until I find one that gives me a remainder of 3. Right, whereas the second one, it says when you divide X by 10, you get Y with remainder 4. Okay. And then they want to know what an X is divided by 5. So what I could do is just make up a number. Okay, what's a number that when I divide by 10, I get 4 left over? Let's see. 10 divided by 10 just gives me 1. 11 divided by 10 gives me 1 remainder 1, right? Like this. And I might start seeing a pattern here that, I want something that ends in 4. 14 divided by 10 gives me 1 remainder 4. So I'll just take 14 as my X. So then I say, okay, 14 divided by 5 is a 2 remainder 4. It's kind of a silly question when you think about it, because 5 goes into 10. So if I have something that's 4 more than a multiple of 10, it'll also be 4 more than a multiple of 5 by definition. Okay. So these aren't the hardest number properties questions you'll ever see, but what I'm trying to highlight in these is what you can notice very early on. What ones it could be, and I'm going to have to evaluate the answers and see which one fits some criterion, or I'm going to have to test them. The other one is a must be. What is the remainder? Which means any number you pick, even if I picked 4 itself, right? I could have a 0. I could have a quotient of 0, 0 remainder 4. And that would work. When I divide 4 by 5, it goes in no times and there's 4 left over, right? So no matter what I have, I'm 4 over. Okay. What about something different? What can I notice early on this one? I've got these nested radicals. 2 plus the square root of 2 plus, wait, the square root of that, oh, plus, right? What's going to happen here? How can I narrow this down? Are there any answers that don't make any sense early on? Okay, I'm seeing A and B are out. A, I understand, right? Because root 2 is right here. So if I just ignore all the rest, that would be A. I can't ignore all the rest, so it's not A. How can I disprove B? Is there a way to do that? What about this? What if I ignored all the radicals entirely? What if I just said, what's the square root? And again, this is not likely to be the answer, right? But what if I just said, what's the square root of 2 plus 2 plus 2 plus 4? 4, 6, 8, 10. I'm not saying this is the right answer, of course. I'm saying this is the wrong answer. But would you expect the right answer to be bigger or smaller than that? How do we know, right? What's bigger, the square root of these things or them themselves, right? Like if I took these root bars off, wouldn't that be making all these numbers bigger? So we actually know this is too big. Root 10 is just over 3. So we know our answer has to be smaller than 3. Can't be these. 2 root 2, that's pretty close. Root 2 is 1.4-ish, so this could be around 2.8. That seems plausible. This is 2. From there, I might have to prove it, but I can get down to 2 pretty quickly, right? Just from using those things. From here, I might actually work from the inside out, right? And say, okay, 2 plus root 4 equals 2 plus 2 is 4. So that's this. This here is the square root of 4. And then I have 2 plus root 4 again is 2 plus 2 is 4. Right? So, so what I'm saying is, okay, this here is 4. And I'm saying 2 plus the square root of 4 is 2 plus 2 is 4. So now I've got 2 plus square root of, yeah, am I doing that right? Square root of 4 in here. So what's that going to get me? Yeah, I'm just going to get square root of 2 plus 2, which is a boring old 4. After all that work, it's just 2. Who knew? But we might know that it's going to be bigger than root 2. And we might know it approaches something like 2 because we're saying, all right, 2 plus a little less, but that to that is a little less than that is less than that, right? So it's certainly getting smaller and smaller. And all this ends up being enough to add up to just this one. But in the first 30 seconds, we can get rid of a lot of the answers. So question is, if you estimate it'll take 30 seconds, you only have 90 seconds left. Don't you think it's better? Short answer, absolutely not. No, no. You want to get good at estimating, especially because you're assuming you can always find the actual answer. The questions I chose today are ones, I think, because I don't know people's backgrounds coming to these, and because some people are just getting started, and because we have just an hour to be together, and so I don't want to take out some really messy problem. I tend to choose problems that we can solve very quickly. That's not always the case on the GMAT. It goes without saying, I think. And so absolutely not. You want to get in the habit of estimating and thinking through these things. And this is stuff you do within the first 30 seconds. Some of the estimates we're doing only take 5 seconds. And so no, I would emphatically say it is, oh wait, I don't want this one. I would emphatically say that you want to get in the habit of estimation, and it is not better to go straight into calculating. That's the way toward 4-minute crash and burn solutions that we don't want. Okay. Now, very different kind of problem. I think we'll probably, wait, do I have the one I was thinking about? Hold on. Yeah. Oh yeah, this one. Okay. So take a minute just to process this one. This will take a slight, amount of time just to know what they're saying since there's no visual. Okay, so we have a problem where we're mixing oil, vinegar, and water. It's rather plain salad dressing. Where's the basil and the salt? And okay, right, oil, vinegar, water. Maybe that stuff doesn't take up much volume, so we don't care about it. We have 8 cups of oil, 7 of vinegar, and as much water. I guess we have nice running water, right? What's the maximum number of cups of salad dressing he can make? So one principle I want to use here that we haven't talked a lot about yet is the idea of constraints. Where is the strongest constraint, right? I've got oil, water, oil, vinegar, and water. And so in terms of what's restricting my maximum, I could say, well, it's not water, right? Because I have all the water I want. From the water perspective, I can make as much salad dressing as I want. So if I need to have oil and vinegar in a 3-to-2 ratio, which one am I going to run out of first? Right, the oil, right? Oil, I need 50% more oil than vinegar. But I have very similar amounts. So oil is the constraint. Okay. So if I want to maximize the amount I do, and oil is what's limiting me, I basically want to use all my oil if I can. Now they told us we can have fractional cup amount, so we don't have to just use 6 cups of oil. That's how some people are getting A. That's not right. I want to use all the oil. And we can sit there now and start calculating, okay, how much is that? And how many cups of, if there's 8 cups of oil, then what's 2/3 of 8? Don't, stop, don't do that. They're asking in the end, this is a really common principle in GMAT, part versus part whole, right? So they're asking about the whole. What is the maximum number of cups of salad dressing he can make? Now, what fraction of the recipe is oil? If I have 3 parts oil to 2 parts vinegar to 1 part water, right? I've got 3 to 2 to 1 means 3 oil to 6 total. The recipe is 1/2 oil. So if I want to use all my oil and the recipe is 1/2 oil, quick, pull in that answer. Let me put it up. What's the answer actually have to be? It's got to be E. He's going to use all his oil, and that's half the recipe. So when he uses 8 cups of oil, I don't know how much vinegar and water he has. I mean, I figured it out like earlier, but like I don't know it right now. But I know it adds up to 8 cups. We could do it, right? But it's ugly. We'd say, okay, if the ratio is 3 to 2 to 1, we'll call these X's, which is 6X total, right? And then if 3X is going to be 8 cups, then I'd say, okay, then X is, 8/3 of a cup. And so this is going to be 16/3 of a cup, the vinegar, and the water will be 8/3. And guess what? 16/3 plus 8/3, right, is 24/3, which is 8, right? So I have 8 cups plus 24/3 is 8 plus 8 is 16, but I don't want to find that out. It's not necessary. I already know the answer. And so finding ways to narrow things down, to look for constraints, that kind of thing is very important, right? And be careful, if they give you information that you didn't use, often that's a bad sign. Why are they bothering to say fractional cups are possible if they just wanted us to say 6 to 4 to 2 equals 12, right? Now, if they said a fractional cup measurements are not possible, then yeah, that's the maximum. And we have to watch that kind of thing, right? I amply illustrated in the first part of the workshop today what happens when we're wrong right at the beginning. I highlighted the wrong arc. I accidentally wrote shaded instead of, we do these things. But if we don't then notice and revise, then we're done with the problem without realizing it. And so often we'll have that situation where we miss the problem in the first 30, 40 seconds and we don't know it. It's like a job interview that we lost before we sat down, right? I showed up to the job 15 minutes late. I made an offensive joke in the lobby, I don't look professional or whatever it is. Something went wrong and I'm there thinking I'm nailing the interview and asking good questions and answering and all that. And they already have cross my name out, right? And so I don't want to be in that situation when I'm doing these problems. I want to give myself a chance to redeem myself and catch if I have made a mistake, something I can't always do with the first impression, right? I can change my mind and change the answer. But I also want to try to avoid some of those dangers in the first place. Okay. So the question was about why we got the answer we got for vinegar, if we're going to do it this way. The idea is that X would be the total amount of oil we use over the 3X. So 8/3, and we're going to multiply 8/3 by 2 and get 16/3 for the amount of vinegar. Okay, so I'm going to stop there. If you have any questions or thoughts about this, I hope you found this useful. If you want to check out any of our classes, you can always do session 1 for free. Try us out. Stick around if you have anything on your mind. Other than that, good luck with all of your studies and your test, and we hope to see you around.